Welcome to this video on implicit differentiation. We start with a little review of the chain rule. When we write something like the derivative with respect to x of x squared, the derivative is easy to obtain because the variable in the function x squared, which is x, and the variable which we are differentiating it with are the same. So here, obviously, the derivative of x squared with respect to x is 2x. However, when we write something like the derivative with respect to x of y squared, the x and the y, so the variable we're differentiating it with and the variable in the function, they do not match. And it's possible that y is a function of x. So we can think of y as f of x. And in that case, we have a composition of function. So we must use the chain rule in order to differentiate the expression. So temporarily, let's just replace y by f of x to see things in an easier way. The chain rule would say that it's going to be 2 times f of x times the derivative of f of x. We will, for convenience, write the derivative of y squared. So instead of replacing y by f of x, we will just know that y may represent a function of x. So the derivative of y squared is going to be 2y times y prime. Y prime here stands for dy dx. And that's just the chain rule version, if you think about it, of the derivative with respect to x of x squared equals 2x. In previous videos, we've used u to write the chain rule version, but in that case, if you replace u by y, you get the equation we just had before. Here are some basic examples of the chain rule where we are differentiating a function of x, which we call y. Here, in our first example, we have the derivative of 1 over y cubed with respect to x. So it's a ratio. It's tempting to use the quotient rule, but because we have a constant in the numerator, we can do something better, at least easier. The quotient would work, but it's easier if we write 1 over y cubed as y to the minus 3, and in this case we can just use the power rule, actually the chain rule version of the power rule. So the derivative is just minus 3 y to the minus 4 times y prime. You can leave your answer like that. If you don't like to work with negative powers, you can write the answer as minus 3 over y to the 4 times y prime. In the second example, we have the derivative of sine of y. Now here, this is just a chain rule version of the derivative of sine of x. So instead of sine of x, it's sine of a function of x. So the answer is cos of y times y prime. In the third example, we have the derivative of x cubed times y squared. So in the first place, we have a product to differentiate. So we're going to use the product rule. And notice that in the first term, the derivative of x cubed with respect to x is straightforward. X and the variable we're differentiating it with, x, match. So that's just going to be 3x squared. In the second term, we have the derivative of y squared, and there we're going to use a chain rule version of the power rule to differentiate it. So we're done differentiating. Notice that we cannot do anything with y prime, right? Because we don't know what y is, so we just leave it as it is. The only thing that we can do is factor common terms. So if you look at the first, well, the two terms that we get, there's a common factor of x squared and a common factor of y, and we can factor those and get a factored form of our final answer. We will look at a practical problem now which involves implicit differentiation. For the curve given implicitly by x cubed plus y squared minus 2xy equals 2, and that's a curve that appears in your textbook, we want to show that minus 1, 1 lies on the curve. We want to find the equation of the tangent line at the point minus 1, 1. We want to find the local linearization of the curve at the point minus 1, 1. And finally, we want to use that local linearization to find the y-coordinate of the point with an x-coordinate of minus 0.8, which is close to the point minus 1, 1 that is used in the local linearization. So this is a graph of the curve that we are using in this problem. So this is an exact copy of the figure that is shown in the textbook. In red is the point minus 1, 1, and in green is the tangent line that we wish to compute in this problem. Now, to show that a point lies on a given curve, you take the equation of the curve and you replace x and y by the given coordinates. And if equality holds, then the point lies on the curve. So replacing x by minus 1 and y by 1, we get that overall the left-hand side is equal to minus 1 cubed, which is minus 1, plus 1 squared, which is 1, minus 2 times minus 1 times 1. So the minus signs cancel out, and to give us a plus, we get plus 2. So we get minus 1 plus 1 plus 2, and that is indeed equal to 2, which shows that this point lies on the curve. Afterwards, we want to find the equation of the tangent line at the point. The first thing to find is the equation for the derivative of the curve at any point, and then we want to find the derivative at that point to get the slope of the tangent line. So to get the derivative of the curve at any given point, we use implicit differentiation. So we take derivatives with respect to x on both sides. We apply derivatives to every single term on the left-hand side. The derivative of 2 is 0, because 2 is a constant function. The first term, x cubed, well, to differentiate it with respect to x, that's fairly easy. It's just 3x squared. The second term, y squared, since y is a function of x, we consider y as a function of x. And that means we need to apply the chain rule, so that's going to be 2y prime. And for the third term, we'll need to use the product rule. So we get 3x cubed plus 2y prime minus, and then it's 2y times the derivative of x, which is 1, plus 2x times the derivative of y, which is y prime. Now we can remove the brackets. And on one side, we'll keep the terms that only have y squared in them and put the other terms on the other side. So you see that on the left-hand side, I have the terms that have y prime in them as a factor. We will factor out y prime, and finally, we will solve for y prime in order to get an expression for the derivative at any point xy. So to get the value of the derivative or the slope of the tangent line, I need to replace x and y by the coordinates of the point. So this is what we're going to do. We're going to replace x and y by minus 1 and 1. If we do this, we get minus 1/4, which is the slope of the tangent line. It makes sense if you remember the figure that we've shown before. The line in green was the tangent line. At least we saw that it was decreasing, so it makes sense that our slope here is negative. To get the equation of the tangent line at minus 1, 1, I can use the point slope equation for a line. So we're given a point and a slope, so it's natural to use the point slope equation, so which is of the form y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of the point. And if we replace m, x0, and y0 by their values, we get this. As you can see in the bracket, I am getting x minus minus 1, so that becomes x plus 1. And we can leave our equation like that for the equation of the tangent line. So we're done here. If you prefer, you can solve for y if you're not comfortable giving an answer where y is not alone on one side of the equality sign. If I want to find the local linearization of the curve at the point minus 1, 1, well, that's very easy once we have the equation of the tangent line, because the local linearization is just the function whose graph is the tangent line. So all you need to do is take the equation of the tangent line, solve for y, and call your y L of x, because we use L for linearization. So we get that L of x is 1 minus 1/4 of x plus 1. Now, the advantage of having the tangent line and the local linearization at a given point is that they can be used to approximate anything that we want to know about the curve itself. So for example, we could use the local linearization to approximate the y-coordinate of a point with an x-coordinate of minus 0.8 when we're close to minus 1, 1. We're saying close to minus 1, 1 because the tangent line and the local linearization is obtained at that point. So we need to be close to that point so that the information that we're retrieving from the tangent line or the local linearization makes sense. Otherwise, the approximation is not good. So for example, any point on the local linearization would be approximate to companion points on the curve. For example, a point with an x-coordinate of minus 0.8 on the local linearization curve would be an approximation to a point with an x-coordinate of minus 0.8 on the exact implicit curve. So by computing L of minus 0.8, which is the y-coordinate of a point with an x-coordinate of minus 0.8 on the local linearization curve, I'm going to get an approximation of the y-coordinate of a point on the implicit curve. So by computing L of minus 0.8, we get here 1 minus 1/4 of x plus 1, x being minus 0.8 here. So overall, we get 0.95. So the point minus 0.8, 0.95, it lies on the local linearization curve, or the tangent line if you prefer, and it is very close to the point with an x-coordinate of minus 0.8 on the exact implicit curve. So if you remember, this is in blue the curve representing the implicit curve. In green, it's our tangent line, or the graph of our local linearization at minus 1, 1. If we magnify that curve at minus 1, 1, we get this. So in green, it's still the tangent line, or the graph of the local linearization. And you see that minus 0.8, 0.95 is a point on the green line, so on the local linearization curve, and it is very close to the exact point, minus 0.8, 0.98 on the implicit curve. So we're making an error of 0.03 with our approximation, but it's a fairly good approximation, again, because the local linearization, or the tangent line, is a fair approximation of the curve at the point where it was computed.